All right, so we're going to continue with deriving new shapes. Now we're going to look at a circular loop of wire. So we have our circular loop. Once again, we're going to follow the convention that we did when we looked at the electric fields of circular loops. So we're going to observe on the z-axis. So we have our delta L, which is going all the way around here. It has some radius r, and we can see that we're going to be measuring from some theta. And we go to our observation. We have our r vector and then our delta b. So we have a wire with current is twisted into a loop. And we will look at the field. Along the axis of a loop. And it turns out this is actually a really applicable situation. So I know sometimes in this class it feels like there's these strange scenarios, but loops of current carrying wires and the magnetic fields associated with them are a key component of lots of different types of circuits, and there's some really interesting physics associated with it, and we will get into that in this semester. Okay, so we have our wire twisted into a loop, so let's start going through our steps. So step one, let's get some more pictures going. Cut up the distribution. Into pieces and draw delta B. Okay. So I think this makes a lot more sense to do a side angle view, mostly because, you know, I don't draw well in 3 dimensions and can really get a feel for what's going on. So we would have our z-axis here. This is the loop. If we think about the loop, then the current's going to come right out towards you, loop around, and then go into the page. So out of the page and then back into the page. So if we look at our observation point, and here we have our r hat, and r is once again equal to x squared. In this case, it's going to be plus r squared for the radius of the circle. And our magnetic field, I'm going to dissect this. Delta B will be going in this direction. And if we were to break this into components for delta B, delta BZ and delta B perpendicular. All right. And so just something to note, the angle between delta L and r hat is 90 degrees for every location on the ring. Which makes sense. Rings are very symmetrical. So step 2, write the expression for one piece. So working out delta B for delta L is a little complicated. I'll show you what it looks like. And we're going to see that we can be a little bit tricksy and save ourselves some work. Because if we were just to write it out, we would see that delta L is equal to r cosine theta plus d theta r sine theta plus d theta. 0 minus r cosine theta r sine theta theta, or 0. And our r vector is 0, 0, z minus r cosine theta r sine theta 0. Yuck. But we can see that this is actually a very symmetric situation. And so the delta b's, or the delta by's on one side, are going to cancel the delta by's out on the other. Likewise are the delta bx's. So all we're going to see is what is in z. So let's just go ahead and say by symmetry, delta by's on one side cancel the other. And same goes for delta bx's. All right, only need to be concerned with z. Okay, so now that we've made our lives a lot easier, let's just keep going. We're going to put the origin is at the center of the loop. So r is equal to 0, 0, z minus 0, r, 0. So this is equal to 0 minus r, z. And our magnitude is equal to r squared plus z squared to the 1/2. And r hat is equal to r over r, which is equal to 0 minus r z over r squared plus z squared to the 1/2. And just like we did with the loop before, the location depends on theta. So delta L is equal to minus r delta theta, 0, 0. And B is equal to mu naught over 4 pi I delta L cross r hat over r squared, which is equal to mu naught over 4 pi I minus r delta theta, 0, 0, crossed 0 minus r z over r squared plus z squared to the power of 3/2. And again, we're just going to pull those vectors out and cross them separately. Minus r delta theta, 0, 0, crossed with 0 minus r z is equal to 0 z times r delta theta, r squared delta theta. And we only need z. So Bz is equal to mu naught over 4 pi I r squared delta theta over r squared plus z squared to the power of 3/2. And so step 3, we're going to add them up. Bz is equal to the integral from 0 to 2 pi to take us all the way around the circle, mu naught over 4 pi I r squared d theta over z squared plus r squared to the power of 3/2. Now we see that this is the only factor that has theta in it. So this becomes mu naught over 4 pi IR squared over Z squared plus R squared to the power of 3/2 integrated from 0 to 2 pi d theta. And the integral from 0 to 2 pi d theta is equal to 2 pi, which makes sense. You just go all the way around the circle. And so from here, we get the magnetic field of a loop. B loop is equal to mu naught over 4 pi 2 pi r squared times I over Z squared plus R squared to the 3/2. All right, so let's check out our results. I'll leave this up for a little bit longer so you can make sure to write that down. Okay. So step 4, check results. The units, Tesla meters over amps times meters squared amps over meters squared to the 3/2 is equal to Tesla. And if we draw this, what we would see, if you've got a current carrying wire, you've got your B field in this case coming out. R hat points in towards the center. Delta L goes out around, radius of R. And we can see, once again, we see a right-hand rule here as well. You go in the direction of current for this current carrying loop, and your thumb will point in the direction of the magnetic field. So at the special case of Z being equal to 0, which would be dead center, B is equal to mu naught over 4 pi 2 pi I over R. And you should prove this to yourself. All right, so there's another special case if you're very far away from the loop. So Z is much, much bigger than R. So mu naught over 4 pi 2 pi R squared I over Z squared plus R squared to the 3/2. And because we're very far away, then essentially Z is much, much bigger. So this goes to 0. And so we get mu naught over 4 pi 2 pi R squared I over Z cubed.